Sa se la Brunella viene stamattina? Sa se la Brunella viene stamattina? No? Ma va! Ma guarda l'aereo Luna. Okay, perfetto. Good morning, everyone, the few of us that survived yesterday. And welcome to the last day of presentations. So let's start with research fellows. The first one will be Matteo Righetti with mixed materials membranes for separation of two components, CO2, CH4 gas mixture. So the stage is yours. Sì, destra. Ah, qui deve partire. Ok, F5. Perfetto.
Hi everyone, good morning. I'm Matteo Righetti and I'm a research fellow at the University of Turin, and today I will talk about my master's degree thesis project entitled Mixed Matrix Membrane for Separation of Two Components CO2 Methane Gas Mixture.
Non va? Vado, sgnacco io, però mi sembra un po' complicato. Non funziona? Scusa.
Okay. No, scusami. The carbon dioxide methane separation is mandatory in industrial process like natural gas sweetening, biogas refining, oil recovery enhancement, and landfill gas purification. In this process, methods like chemical absorption, pressure swing absorption, and cryogenic distillation are now in use. This method suffers from some limitation and faces some challenges like the use of high amount of solvents, high implant management costs, poor separation efficiency, and high energy consumption. Membrane model separation in this scenario result as a game-changer technology thanks to an easy-to-make equipment, reduce ordinary maintenance, reduce ambiental impact, and low production cost. In order to be applied in the gas separation field, a membrane needs to satisfy some requirements, such as chemical stability, thermal stability, mechanical stability, need to be made out of a material with an easy processing procedures, need to possess high permeability and high selectivity, two properties that defines membrane separative performance. Both polymeric membranes and inorganic membranes suffer from intrinsic limitation and can satisfy at the same time all these requirements. From the 1990s, in the gas separation fields appeared mixed matrix membrane, a membrane made out of a continuous phase and a dispersed phase. The dispersed phase can be made out of different additive like organic additive, inorganic additive, metalloorganic frameworks, graphene-derived additive, and the additivation is carried out in order with the aim to obtain a tunable permeability and an increased selectivity. For this the result is obtained exploiting molecular sieving effect, facilitated transport, and variation of polymeric chain packing structure, or free fractional volume increase. The purpose of the work is to develop a novel mixed matrix membrane for the separation of carbon dioxide and methane using cyclodextrin derived additive. And today I will talk to you about the additivation effect on membrane morphology, mechanical properties, surface wettability, and separative performance. We use a polymeric matrix of polyethyl sulfone modified with a cardio group, and we additivated it with beta cyclodextrin nanosponges, obtain cross-linking beta cyclodextrin with carbonyl dimidazole in a ratio 1:4. Two types of membranes have been produced, a blank membrane and a mixed matrix membrane. Here is reported the optimized production process of the membrane. Every solution casted have been produced in DMF, and two-step thermal treatment have been applied to a blank membrane and to the mixed matrix membrane. The additive quantification have been carried out using a thermogravimetric analysis, and a content of 3.83% weight by weight have been determined. As you can see from these same images, the thermal treatment is mandatory to obtain a membrane able to produce selectivity towards CO2 and methane, and a membrane with a compact and dense structure. After the additivation, you can see the membrane morphology is conserved, and beta cyclodextrin nanosponge particles are present in the bulk of the membrane. Here is the section, and a few of them appears also on the surface of the membrane. The stress strain test revealed that after the additivation, a reduction of fracture stress and strain to fracture globally reduced the polymeric matrix ductility. Contact angle measurements revealed that after the thermal treatment and after the additivation, we observe a progressive enhanced wettability with a reduction of the contact angle. In the first case, after the thermal treatment, the increase can be justified by the transition from a rough surface of the membrane to a smooth surface of the membrane. While in the second case, the hydroxy group of the additive not involved in the cross-linking process can develop a hydrogen bond with water droplets used as probe in this kind of analysis. Here is present the schematic implant of the bench that we use at Polytechnic of Turin to carry out permeability tests. As you can see, we perform two types of tests, an open system test on the blank membrane and a closed volume test on the mixed matrix membrane. The two tests differ from, the first test is most suitable for membrane with high permeability, and they differentiated by the sensor used to acquire data to then convert in permeability results. An instrumental setup validation has been carried out using a closed volume test on a commercial matrimid membrane, and a CO2 permeability of 8 bar have been registered in accordance with the supplier specification. As you can see, the blank membrane possesses a high selectivity at the point that no permeability data are available for CO2 for pressure difference above 5 bar. The reason is that for this pressure difference, the volumetric flow rate of the CO2 exceeded the maximum value that the instrument, the sensor, can detect. After the additivation, as we can see, there is a reduction of permeability of both species. There's a crossover point. Let's say that this is a crossover point, after which the trend of permeability for CO2 and methane are inverted. The origin of this phenomenon is still unknown. As we can see from this plot, after the additivation there is an increase in ideal selectivity, and for every pressure difference explored, the mixed matrix membrane performs better with respect to the blank membrane. So after the additivation, we obtain a membrane with an enhanced ideal selectivity. Despite not being able to overcome both the 1991 and 28 limit of the Robinson plot, the mixed matrix membrane that we produce possess enhanced separative performance, and nowadays polymer additive rush optimization are ongoing in order to explore different additive concentration. So, in conclusion, we produce a mixed matrix membrane that uses beta-cyclodextrin derivative as additive. No alteration of morphology have been observed after the additivation. We observe an enhanced wettability, but a reduced ductility of the polymeric matrix. The membrane itself possesses enhanced separative performance. As I said before, the polymer additive rush optimization are ongoing. Once find the most performing, the better performing mixed matrix membrane, temperature influence tests are planned. And in the end, we are aiming to test our membrane with a real gas stream to separate CO2 and methane from biogas stream or natural gas stream. I want to thank my research group, my colleagues at Politecnico, and the organizing committee, and you to be here today. Thank you.
Thanks, Matteo, for the nice talk. So, if you have some questions, it's too early, maybe. And so, just a few curiosities, and have you thought to use maybe other types of cyclodextrins?
Yes, we evaluate the possibility to use alpha-derived cyclodextrin nanosponges, but this type of additive is more suitable for gas storage application and not for gas separation application.
Okay, and maybe have you thought about reprocessability of these kinds of membranes or not?
Yes, it's not an aspect that I work on, but there's some talks about the reuse of the membrane. The blank membrane can redissolve in DMF and recast to produce a new membrane. For the mixed matrix membrane, there's the possibility to recycle the membrane, but the separation of the nanosponges, the additive, have to be carried out.
Okay, let's thank again Matteo. And let's move on with the second speaker, Emma Contini, please, on stage. She will talk about mechanochromics performances of perilene diimide top polyurethanes, covalent bonding versus blending approaches. The stage is yours.
Hello, everybody. Today, as I don't remember your name, but you said, I will talk about the mechanochromic performances of perilene diimide doped polyurethanes, the covalent bonding versus the blending approach. So, as the name suggests, I will talk about mechanochromic polymers, and in the literature are reported many ways in which one can make mechanochromic polymers. Among all these approaches that allow us to develop a material that responds to the application of a stress with a variation in its spectroscopic properties, we chose to use the rupture of molecular aggregates approach. And the major advantage of this approach is that it allows us to use aggregochromic dyes. And these dyes are fantastic for the development of mechanochromic polymers, since when they are in the aggregated state, so the state on the left, and when they are disaggregated, so in the monomeric form, they present a different emission spectrum. And since this transition from the aggregate to the monomer can be triggered by a shear stress like the one induced by the strain of macromolecules when we stretch them, we can employ them in various polymeric matrices to have mechanochromic properties. Moreover, since the monomer and the aggregate emit in different regions of the spectrum, we can use the ratio between the emission of the monomer, which is in the blue region of the emission spectrum, and the aggregate to evaluate the strain that is applied to the material, of course, if there is a mathematical relationship between these two functions. This approach is not new in the literature. It's over like 20 years that has been developed. However, in the last few years, the research has focused on the addition of these dyes directly to the main polymeric chain. And this approach is interesting because theoretically, if we add the chromophore directly to the polymeric matrix, the shear, we don't need to have a shear-induced disaggregation, but it's just the direct application of the stress that triggers the disaggregation. However, since at the moment there aren't many direct comparisons between this direct incorporation and the dispersion approach, we wanted to evaluate if going through all the trials and tribulation of polymeric synthesis was worth the cost, let's say. So to do that, we compared the mechanochromic performances of main chain thermoplastic polyurethanes containing a perylenediamide derivative in the main polymeric chain, and the same thermoplastic polyurethane containing the same dye but dispersed. Luckily, I didn't have to do all the trials and tribulation of the synthesis because we collaborate with the Dalcanale group of the University of Parma, which went through all of that. We then received these polymers and blended them with a commercial polyurethane to improve their mechanical properties. We made 3 dispersed blends with different concentration of the dye to evaluate the effect of the concentration, and the same was done with the main chain blends, but with 2 different concentrations. We prepared films with these materials through solvent casting and compression molding, and then we characterized them through both thermomechanical characterization and, at least for me more interestingly, from the mechanochromic point of view, using a setup similar to the one represented in the image. So, going to the mechanochromic response, we can see that for all the blends under analysis, both dispersed and main chain, we have a mechanochromic response because the spectra changes when we strain the sample in going in this color scheme from the red spectrum to the green one, which is over 1000% of deformation. But we didn't just want to make a mechanochromic polymers. I mean, many can do that. We wanted to evaluate if the dispersed or main chain approach is better. And to do that, we needed to move to the ratiometric emission intensity versus the strain plot. And luckily, we saw that these data could be fitted versus the strain with a linear function. And this is great because we can use the slope of this linear function to evaluate the sensitivity of the method. And we saw that for both the main chain and the dispersed blend, the highest sensitivity was reached by the material having the lowest concentration of the dye. And this result can be attributed to the fact that systems displaying low concentration of the dye tend to form smaller aggregates. And the smaller aggregates are easier to disaggregate compared to larger size aggregate. Different result, I mean, different from the interesting point of view, can be seen when we look at the sensitivity of main chain and dispersed blends having the same concentration of the dye. Here we can see that main chain and dispersed blend having the same concentration of the dye basically show the same slope, so they show the same sensitivity. And this result can be attributed to the fact that in main chain blend, we have a 2-component system where we have a low molecular weight thermoplastic polyurethane bearing the chromophore in the main chain, and an high molecular weight polyurethane that is inert. It just has to carry the load when we strain the sample. So what occurs in this material is that when we stretch our material, the high molecular weight polyurethanes carries the load, whereas the low molecular weight polyurethane is strained by like a shear-induced mechanism. And so, since this mechanism can be compared to the dispersed one, which is a shear-induced one, we obtain materials that have the same sensitivity. Different results are observed when we look at stress relaxation experiment. Here I have reported the result obtained for both main chain and dispersed blend having the same concentration of the dye. And what we can observe is that when we stretch our material, so in the load phase of the stress relaxation experiment, for both blends we observe a disaggregation of the dye, so an increase in the monomer over aggregate emission intensity. And then for both blends we observe a reaggregation phase that occurs during the whole stress relaxation process. However, if we compare main chain and dispersed blend, we can see that main chain blends follows more linearly the stress relaxation process. This result can be attributed to what occurs during a stress relaxation experiment. I mean, when we stretch our sample and we fix the deformation, we have an instantaneous re-entanglement process that is driven by entropy. But as mentioned earlier, our chromophore-bearing thermoplastic polyurethane has a low molecular weight, and so has a higher mobility compared to the second thermoplastic polyurethane that actually carries the load. So when we fix the deformation, this component has a higher tendency and easier reaggregation process, thus leading to a faster reaggregation of the dye. Conversely, in dispersed blend, the reaggregation that occurs, of course, is probably caused just by a strain-induced crystallization process that decreases the free volume present in the material, thus leading to disaggregation. So, in conclusion, we have that for this material, we have developed both dispersed and main chain blends that are mechanochromic. However, if one wants to develop a material that is sensitive mainly to strain, it is better to use dispersed blends since they are cheaper, easier to integrate, they can be added to many different polymeric matrix. And they display, of course, a similar sensitivity compared to main chain blend. On the other hand, if we want to develop a material that is mainly a stress sensor for a long period of time, it is better to use main chain blend since they display an improved responsiveness in stress relaxation. I want to thank, before leaving, all my co-workers from the Polymer Science and Biomaterial Group of the University of Bologna, and you for being here. Thank you for your attention, and if you have questions, I'm here to answer them.
Thanks, Emma, for the nice talk. So the audience have questions about it?
Oh, thank you very much for the nice presentation. I was wondering about the reversibility of this kind of system to measure the mechanochromic effect. Like, are they reversible?
No, not very much. I mean, if we go back, and we look at the strain that we need to reach to have a sensitive material that is mechanochromic, we need to reach really high deformation. And at this deformation, it is hard to have a on-off system that is instantaneously reversible. But if we look at stress relaxation, we can see that there is a sort of reaggregation process. However, since the material is deformed over its elastic deformation range, it depends on what you consider as a reversible. If you want a material that is reversible in the elastic deformation range, this is not the case. If you are okay with going in the plastic deformation range and so not reaching complete redimension of the sample, it is reversible.
Okay, thank you very much.
Thank you.
Other questions? If not, let's thank again Emma. And move on with Luca Gargiulo, who will talk about microwave-assisted extraction of hemp seeds, oil, and its use for food packaging systems. So.
Good morning to everyone. I'm Gargiulo Luca, Research Fellow at TPCB CNR in Pozzuoli. I will talk about microwave-assisted extraction of hemp seed oil and its use for food packaging. Hemp is a very promising plant, rich in bioactive molecules mainly found in leaves and flowers, and a very rich lipidic portion mainly found in seeds. In fact, we focus on seeds thanks to their high oil amount, rich in omega-3 for what concerns alpha-linolenic acid and omega-6 for what concerns gamma-linolenic acids. What are the aims of the research? At the first point, we have the oil microwave-assisted extraction process and the yield optimization. On the second point, we have the evaluation of this oil antioxidant activity. And thanks to thinking about future oil application as additives for thermoplastic polymers such as PBS, on third point we have the film production of PBS oil-based film. And on the last point, so in order to evaluate the applicability of this film for food packaging, different tests of additive release in food simulants were carried out following the European Regulation Commission in a preliminary way. So, as regards microwave, this is composed by different vessels that are loaded with hemp-seeds in powder and hexane as extracting solvent. At the end of the process, we obtain the oil in the extracting solvent that is dry by rotavapor in order to obtain the final product. So, different extraction tests were carried out at different times. So, starting from 2.5 minutes until 1 hour and compared to classical extraction method like Soxalet. These oils were first thermally characterized. If we look to TGA thermograms, we can see that we have no significant differences among the oil. We have a starting weight loss around 320 degrees of about 10–15%. And if we look to Soxalet oil, we have a peak around 415 degrees that could be due by decarboxylation of fatty acids. If we look to phthir, we can see that despite the different extraction method, we do not have differences in the structure, as we can see by the main functional group. So, focusing on extraction yield, with microwave we obtain extraction yield comparable to Soxalet, but using an extremely shorter operating time. And for what concerns the antioxidant activity that was evaluated through DPPHSA, also in this case we obtain good antioxidant activities value compared to Soxalet and compared to literature. Because with the microwave we have different advantages such as mechanical action given by the vibration of the molecules that allow the breaking of cellular membranes, and at the same time we have an intrinsic heating process that allows us to work with constant and controlled temperature. This is not possible, or it's difficult with Soxalet, in which we have very long extraction time. So, thinking about the future oil application, we thought to use this oil as additives for thermoplastic polymer. In this case, we choose PBS because allow us to work with relative lower temperature of about 113 degrees, so close to PBS melting temperature. But before using the oil as additive, these oils undergo to an heating process with TGA until 115 degrees for 20 minutes in order to evaluate the antioxidant activity before and after this heating process, because we want to ensure that this oil didn't undergo to structural changes. So if we look to the table, we can see that the antioxidant activities values doesn't change before and after the heating process, so we were sure to use this oil as additive for PBS. If we look to the first image, in which we use the higher oil concentration of about 2.5%, in this case we obtain a dishomogeneous film, so too much plasticized by the presence of the oil. In fact, PBS is pushed toward the external portion with huge oil exudation phenomena. So we reduce the oil concentration to 1%. In this case, so in the second image, we obtain a quite homogeneous film but with clear oil exudation phenomena. So reducing the oil concentration to 0.5%, in this case we obtain an homogeneous film with reduced oil exudation phenomena, and so we decide to work with this last formulation. So these films were thermally characterized through TGA. If we look to the T onset value, we can see a significant reduction in T onset respect the pure PBS. This is due by the presence of the oil and by oil plasticizing effect. In this case, oil seems to work as a PBS thermal pro-degrading agent. So in a preliminary way, different tests according to European Regulation Commission were carried out of additive release in food simulants. So to start, in a preliminary way, we use this water solution with ethanol at 10% that is suitable for simulant A, that is due for food like fruits, vegetable, meat, and eggs. If we look to the graph, in a preliminary way, we can see that for the system, so PBS obtained with the oil, starting from 15 minutes until Soxalet, we can preliminarily say that we obtain a quiet release of the additives in the food simulants. For what concerns the first system, is evident a more push release of the additives in the medium. So we can preliminarily say that this first system is not suitable for this type of food. And now we have to perform the other system to obtain better results. So to conclude, we can say that we obtain extraction yields comparable to Soxylate, but using an extremely shorter operating time, good antioxidant properties of the extracted oil, and a promising MC's oil application in food packaging system for what concerns the simulant A, so for food like fruits and vegetables. So for what concerns future perspective, we have the evaluation of PBS oil-based film and, antioxidant and mechanical properties. We have the use of alternative extraction solvent, extraction on hemp inflorescences, and the evaluation of film application with other food stimulants. So thanks everyone for your attention, and special thanks to my research group.
Thanks, Luca, for the nice talk. Do you have questions for him? Many questions. Good.
Thank you for the nice talk. I was wondering if you are also thinking to change the matrix of the system, the polymer matrix. Thank you.
Thank you for your question. Yes, sure. We could use other thermoplastic polymers such as polyhydroxyalkanoates, because we had experience on this type of polymer that were functionalized with different types of oil. In that case, also to overcome structural problems of this polymer. So we want to use other polymer, yeah. So in particular, polyhydroxyalkanoates.
Over here.
Thank you for the presentation. I have two curiosities. The first one is, have you in mind already some alternative solvents for the oil extraction? And the second one is, how are you planning to characterize the mechanical properties? So if, do you have in mind any specific tests?
Okay, thank you for your question. So for the first one, now we are focusing on only on hexane, but as a future perspective, we want to use principally solvents like hexane, but at the same time we want to focus on bioextraction solvent. Now we are in a phase of study to to choose one of them. For the second question, we want to do only a tensile test. So in order to evaluate if the oil has an effect also on plasticization of this film. So thank you.
Other questions?
Thanks for the presentation. I have just a curiosity. How did you prepare the films? It's hot melting and then press?
With press.
Oh.
So we have temperature of about 113 degrees and 3 pressure steps. So first heating, 2 minutes with 0 tons, 2 minutes 15 tons, and 2 minutes 100 tons, and after a faster cooling process.
Okay, so you mix your PBS
Yes,
with oil?
we prepare a blend with PBS and oil in chloroform.
Okay, thank you.
Thank you.
Perfect. So let's thank again Luca. And welcome to the stage to Chiara Gnoffo. She will talk about identification of microplastics in different mixtures and blends through pyrolysis, gas chromatography, mass spectroscopy. So.
Good morning, everyone. Today I will show you my work about identification of microplastics in different mixtures and blends through pyrolysis, gas chromatography, mass spectroscopy. This work is part of an European project, the Minagris project, whose aim is to evaluate and assess the macro, micro, and nanoplastics in agricultural soils. They extracted from different fields on the basis of different weather, crops, and the plastic use through Europe, and they want to assess the type of plastics that are most commonly in the farms. From our side, we are focusing on the use of pyrolysis gas chromatography mass spectroscopy in order to do tests on microplastics and nanoplastics. So in order to do that, we decided to test some polymers which are most commonly used in agriculture, and then do a qualitative analysis. After that, we wanted to evaluate the limit of detection of this instrument, and so we tested also some blends with different amount of polymers in that. In literature, there are some works about identification of microplastics in samples. Usually, they use some techniques as infrared spectroscopy or Raman or differential scanning calorimetry. But in this case, we work with low amount of plastics, and moreover, these techniques sometimes suffers from background noise or organic matter that we are expecting to find into samples. So firstly, we optimize the parameters of the pyrolysis with a pyrolysis final temperature equal to 600 degrees C. Regarding the chromatography part, we used also on the basis of the literature and on the type of polymers that we will receive a ramp from 70 degrees C up to 300 degrees C. Regarding spectroscopic parameters, we used an interface temperature equal to 200 degrees C. Then we did some tests on 5 the most common type of polymers used in agriculture, and we decided to identify them by their markers. So, for example, for polyethylene, we decided to look for the highest peak related to the 1D scene. For polypropylene, also in this case, the marker will be the 2,4-dimethyl-1-heptene, as well as for polystyrene, its precursor, the styrene, for polyamide, the caprolactam, and finally for polycarbonate, the bisphenol A. We did tests on 70 different types of mixtures, and in the end, now I'll show you the result on the overall mixes, where we can see that we are still able to identify the peaks. The parameter that we have to evaluate in order to be able to do a qualitative analysis on the mixes is the signal to noise ratio. In this case, it has to be higher than 3. Then we extruded some blends at 190 degrees C with different weight percentages from 10 up to 19% of polyethylene, polypropylene, and polystyrene. We used, on the basis of the literature and on the detector saturation, different peaks for polypropylene and polystyrene that seems to be better for quantification. For polyethylene and polypropylene blend, we can see that with a higher amount of polyethylene, its peak increases. And we saw that we were able to do a qualitative analysis for polyethylene and polypropylene, while the quantitative analysis is always possible for polypropylene and certain for polyethylene above 10%. In this case, for quantification, the parameter that we have to evaluate is always the ratio between signal and noise, but in this case, it has to be greater than 10. For polyethylene and polystyrene blend, we saw that also in this case, the qualitative analysis is always possible, while the quantitative one is possible for polyethylene and certain for polystyrene above 10%, as well as in polypropylene and polystyrene blend, where the qualitative analysis of PP has been done, while the polystyrene is not detected under 50%. Finally, we did some calibration curves on this result in order to see if there were a correlation between the peak era and the amount of the components in blends. And we saw that the trend can be approximated to a linear fitting, but also to an approximated, to a quadratic approximation. We saw that the coefficients of determination were higher than 0.92 for a linear fitting, and higher than 0.95 in some cases for linear fitting and in all quadratic approximation. So we can say that there is a strong linear correlation between the peak area and the amount of polymer. So in conclusion, we were able to do a qualitative analysis on solid mixtures of polymers and a quantitative one on blends. The focus now will be on real microplastic samples, and we are also dealing with some nanoplastic samples also from the fields. I would like to thank the organizing committee, my colleagues from All Polymer Group, and all of you for your kind attention.
Thanks, Chiara, for the interesting talk. Time for questions? Nothing? And only a curiosity, how you think you can develop the analyzing process for real samples from the fields, from the sea and whatever, because microplastics are in matrices, complex matrices, and how you think you can develop this method for this purpose?
Yeah, they do an extraction method in Switzerland, and they will send me the samples in a mix of xylene and trichlorobenzene. So then we will evaporate it and then test it. But of course, there will be also organic matters, and now we're also looking for additives because from polymers they could be released in the soil. So we have to evaluate also that.
Okay, thanks. Very, very interesting. Thanks again, Chiara. And welcome on stage to Eleonora Lorenzi, who talk about developing of polypropylene-based materials with flame retardance properties for 3D printing. The stage is yours.
Good morning, everyone. The research work I'm going to be presenting today had the aim to develop a polypropylene-based material with flame retardancy properties for 3D printing, and to compare the properties of this material when processed through 3D printing or through a more conventional processing technique like compression molding. This to assess whether the properties of this material are kept in the 3D printed samples. In the last few years, the application of additive manufacturing techniques has grown a lot, but the choice of materials suitable for this kind of techniques is still very limited. And this is why there is a need to develop new materials suitable for additive manufacturing with better properties and, most importantly, specific functionalities. Amongst the different types of additive manufacturing techniques for thermoplastic polymers, the fused filament fabrication is one of the most used. And this method involves the construction of a desired object through a layer-by-layer deposition of a molten thermoplastic filament extruded through a nozzle. But not all polymers are suitable for this kind of process. In fact, the conventional materials used for 3D printing are always amorphous or low crystalline polymers, like ABS or PLA. Very rare, instead, is the use of polyolefins like polypropylene. In fact, polypropylene, due to its semi-crystalline nature, during the cooling phase, it undergoes a high volumetric shrinkage, and this leads to a distortion, delamination, and therefore detachment of the object from the printing platform. Moreover, polypropylene shows a very strong Newtonian behavior, while materials suitable for 3D printing should have a non-Newtonian behavior. And finally, polypropylene also shows very low adhesion to any material that is not itself polypropylene, so this leads again to problems of detachment of the object from the printing platform. All these problems mean that there are very few examples of polypropylene-based filaments for 3D printing. And in any case, these filaments are never functionalized. But at the same time, polypropylene is one of the most widely used polymers in many areas, thanks to its low cost and excellent properties. And this is why it's very important and interesting to be able to introduce its use also in additive manufacturing techniques like 3D printing. And this is exactly why we chose polypropylene as our polymer matrix. In particular, we used a random copolymer of polypropylene and polyethylene. To improve the flame retardancy properties, we used a nanoclay, a 5% of chloride 20A, plus 3% of polypropylene graft maleic anhydride used as compatibilizer. The composite was produced through melt compounding in a co-rotating twin screw extruder, and the extruded material was then cooled in a water bath and cut into pellets. Before starting the production of the filament for the 3D printer, we decided to evaluate the processability and so the printability of this material. And from the complex viscosity curves here reported, we can see how the polypropylene without the nanoclay shows a very strong Newtonian behavior, while the addition of the nanoclay leads to an important increase in the non-Newtonian behavior of the polymer. And this is actually a way more suitable rheological behavior for the 3D printer. In fact, the presence of shear thinning at high shear rates allows the material to have enough low viscosity when passing through the nozzle, while the presence of yield stress at low shear rates allows the material to have enough high viscosity at the exit of the nozzle. So, the filament for the 3D printing process was produced with the extrusion system here reported. And the aim of this step was to obtain a filament suitable for the 3D printer, so with the low superficial roughness, circular section, and with a section of constant diameter of around 1.75 millimeters. And from the same analysis, we can see that we were actually able to obtain such filament. In fact, here we can see the section, which is circular, and that the diameter is perfectly constant. From these other images, we can also see that the nanoclay was well dispersed and distributed in the polymer matrix, and that all the aggregates have sub-micrometric dimensions. For the 3D printing process, different parameters like the extrusion temperature, the printing bed temperature, and the use of different kinds of supports to increase the adhesion were optimized in order to obtain high-quality samples. Every sample has been printed with 100% infill, but different infill patterns have been used in different samples, like you can see in these pictures here. To evaluate the flame retardancy properties of these samples, a calorimeter tests have been carried out. With this analysis, the heat release rate is measured in function of the time. And from these curves, we can compare the 3D printed samples with and without the nanoclay. And we can see how the presence of the nanoclay leads to better flame retardancy properties, with the important decrease in the peak of heat release rate and an increase in the flame out time. Another interesting comparison can be made between the samples obtained through 3D printing or through compression molding. And here we can see how actually the 3D printing process leads to better flame retardancy properties, with again a decrease in the peak of heat release rate and an increase in the flame out time. This can be explained with the fact that the material, when passing through the nozzle of the 3D printer, undergoes a elongational flow. And this elongational flow promotes the nanofiller alignment inside the polymer matrix. And this alignment of the nanoclay allows the formation of a more compact char layer, like we can see in the picture here. And this more compact char layer has better barrier properties for both volatile products and oxygen, so this leads to improved flame retardancy properties. So in conclusion, this work shows that it's actually possible to develop and 3D print polypropylene-based functionalized composites, but most importantly, it shows that the 3D printing process allows the material properties to be maintained, and that it's actually possible to obtain even better flame retardancy properties thanks to the alignment of the nanoclay. In the future, it will surely be interesting to investigate new additives in order to obtain new functionalized polypropylene-based filaments with other specific properties like electrical conductivity, thermal conductivity, or even antibacterial action. I would like to thank the organizing committee, all my colleagues from the All Polymer Group, and of course all of you for your kind attention.
Thanks, Eleonora, for the interesting presentation. Time for questions. Over there.
Hi, thanks for the nice presentation. I was wondering if you were able to print a single layer or if you were able also to print a multi-layer structure.
Thank you for your question. We printed samples for the cone calorimeter tests, so they are 3 millimeters thick. And, but you can choose the height of the samples that you prefer. Of course, the smaller the height, the more quality of the surface you can obtain. So 3 millimeters is, I think, the limit you can go, because if you keep adding layers, these layers have more roughness. So you have a sample with more superficial roughness.
Okay, thank you very much.
Thank you.
Other questions? Over there.
Thank you very much for the nice presentation, and you have all my admiration for working with polypropylene in 3D printing. And I was wondering regarding the question before, if like the limit is really only the surface roughness, or that if you add more layers, then you have got a lot of work of warping of the piece, and you basically are not able to get anything reproducible anymore.
Sorry, could you repeat?
Sorry. No, I was wondering if the problem in adding more than 3 millimeters of plastic is only the surface roughness of the final piece, or that everything starts to warp, like the piece start to warp and detach from the printing bed.
Well, the printing process was really hard because, yes, the sample was detaching from the printing platform already at like 2 millimeters, but with the printing bed in polypropylene and also the use of a special glue made especially for printing polypropylene on polypropylene, we were able to print with no problem these 3 millimeter samples. And so I think you can keep adding layers, but the principal problem for me was the superficial with the superficial roughness, which was really high. And yes.
Okay, thank you very much.
So, thanks again, Eleonora. And welcome on stage to Michele Zanoni, who will talk about two-way shape memory polymer as a platform for light-induced reversible actuation from film to fibers.
Thank you.
Laser? Okay. Hi to everyone, my name is Michele, and today I will show you the work I conduct on light-activate shape memory polymer. Based on their functioning, shape memory polymer can be classified in two main categories, one-way and two-way. One-way require a programming phase and then can actuate only once, while two-way can actuate repeatedly. There are four main categories of shape memory polymer based on the underlying physical principle that govern their behavior. One of the categories is composed of semi-crystalline elastomeric network. In the first image, we can see a semi-crystalline elastomeric network that it is composed of cross-linked amorphous phase and the crystalline domain. If we apply a constant stress to this polymer and then we melt the crystal, we will obtain an elongation of the polymer in the direction of the applied stress. At this point, if we cool the polymer below its crystallization temperature, we will obtain a counterintuitive phenomenon called crystallization-induced elongation. The result is that the polymer elongates, and as a result, the amorphous phase is stretched and with low entropy, and the cross-link are subject to tension as they are away from their equilibrium position. Subsequently, if we melt the crystal that keep elongate the polymer, we will obtain a contraction, and this phenomenon is called melting-induced contraction. We have seen that the shape memory polymer rely on surpassing a transition temperature. This can be achieved by in several ways, or by heating through apply light, electric field, or magnetic field, or by lowering the transition temperature by using, for example, plasticizer or chemical modification. We have chosen to use light. Why we have chosen light? Light can be transported by optical fiber, can travel long distance in vacuum, can be focused on specific area, and based on the wavelength, it is also safe for human tissue. To use light, it is necessary to add a photothermal additive, such as azobenzene. Azobenzene are a photochromic system that undergo isomerization from a stable transform to a metastable CIS form by absorbing UV light. Then the system can revert back by thermal relaxation or by absorbing blue light. The problem is that the half-life of this the CIS form is typically several hours. But there are a class of azobenzene called push-pull azobenzene that has a half-life of the CIS form ranging from second to millisecond due to have an electron donating group on one ring and an electron withdrawing group on the other ring. For our system, we have chosen as functional filler a push-pull azobenzene, and as a shape memory polymer, a triethoxysilane terminate PCl. Triethoxysilane group can be cross-linked in the presence of water, and the reaction is catalyzed by acid catalysis and heat. So at this stage, we have created two different morphology, a film through film casting and the matte through electrospinning. To test the thermal performance, we employ two different techniques. Firstly, by using a thermal camera, we measure both the front and the back side of the sample exposed to light. And from the graph, we can see that both matte and film have a thermal gradient between the front and the back side, but the matte has a gradient that is more pronounced. Has matte scatter light, so only the outermost layer of matte can be heated. Moreover, matte have a thermal insulation property due to a high fraction of air present within them. The second technique was using a DMA machine. We perform a stress strain test on sample, illuminate with different light intensity. Then from the stress strain curve, we derive the elastic modulus, and we plot them against the light intensity. From the graph, we can see that matte has a low apparent elastic moduli, simply due that matte has a high fraction of air present within them. And the second observation is that the matte activates at higher light intensity due to light scattering and thermal insulation properties. At this stage, we took the sample, placed them in a DMA machine, subjecting to a constant stress, and then we exposed.
Increasing was observed, and the increasing PBF content led to an increasing incipient plasticization. In the case of the sample containing 5, 10, and 20% of PBF, there was a strong plasticization, and the increasing PBF content led to a really increase on the strain at break. So now we'll move to the characterization of fiber samples. As you can see, of course, as expected, the increasing collection rate led to a decrease in the average diameter of the fiber. and the addition of the compatibilizer as well as that of PBF cause a change in the diameter of the fibers. Here are the same images of the fiber samples. Comparing those images to the previous one of the bulk, there is a more homogeneous structure with smaller PBF domains, and the increase in the collection rate, it was observed a decrease in the PBF domain size. Moreover, we observed some elongated PBF domains, which are the cause of the increased ductility of PLA. Okay, those are the results of the tensile test on the fiber samples. As you can see, the addition of PBF led to a strong increase in the strain hardening phenomena, and also in this case enhanced a lot the strain at break. And the highest property, let's say, were found for the sample containing 5% of PBF. So if we look at the elastic modulus at this strength and at the strain at break, there is an increase on the first two with the increasing collection rate, but the maximum strain at break was found at intermediate collection rates. So in conclusion, we successfully produced those blends, which were immiscible as expected, but were finally dispersed and compatibilized. The PBF strongly increased the ductility and the toughness of brittle PLA, and the melt spinning process was found to improve the homogeneity and the adhesion of the two phases, and also in this case, PBF led to a higher toughness and higher strain hardening of PLA. Future perspective could be about the MA test or XRD test, but also the evaluation of higher collection rates and a possible subsequent drawing process. So thank you for the attention. I am available for questions, or you can also look at our recently published paper about this topic.
Thanks, Eduardo, for the nice presentation. So, time for questions. Oh, over there.
Just a curiosity, do you have tested the spinability of the blend without Jonkril? And there is this need of using Jonkril or not, on your opinion?
Okay. In a previous work, we evaluated the effect of Jonkril also with other furanoate polymers, always blended with PLA, and it was quite necessary. I mean, there was a strong improvement on the properties. And also in the case of the fibers, there was, much better results with the addition of Jonkril. Moreover, during the melt spinning process, the compatibilization is improved because probably during the simple melt compounding and dot pressing, the compatibilizer didn't react completely due to the short time. And during the melt spinning, it was improved also the compatibilization. Yeah. You're welcome.
Thanks again, Eduardo.
Thank you.
And now move on with postdocs. And the first one will be Giulia Fredi. We'll talk about in situ anionic polymerization of caprolactam for polyamide 6-based thermoplastic composites.
Thank you very much. Hello everyone, this is Giulia Fredi from the University of Trento, and my talk of today will be about the polymerization of caprolactam to produce in situ reactive thermoplastic composites. So thermoplastic composites have a number of advantages over their thermosetting counterparts. In fact, they can be processed with shorter thermal cycles, they have infinite shelf life, and they are also post-thermoformable, thereby increasing the production rate and also their recyclability. However, the high viscosity of traditional thermoplastics compromises the correct impregnation of reinforcements, and this is an issue especially for continuous fiber reinforcements. One of the possible solutions is to go with reactive processing, for example, through in situ polymerization. In this technique, we start from the monomer or from low viscosity precursors, which we inject or transfer in the mold, thereby producing the polymer, the composite, and the component at the same time, and skipping all these intermediate steps. One of the most interesting polymers that can be processed in this way is polyamide 6. In fact, polyamide 6, as you may know, is polymerized by the, starting from its monomer, which is epsilon caprolactam. And this can be done through two main routes. The first one is the hydrolytic polymerization, and the second one is the anionic polymerization. The anionic polymerization can be performed at a lower temperature and takes much lower time compared to the hydrolytic polymerization. Moreover, it does not release any byproduct, so it is suitable for reactive processing and leads to polyamide 6 with a high molecular weight, a high conversion degree, a high crystallinity, and therefore a high elastic modulus. Of course, there is no such a thing as a free meal, so we have also the disadvantages of this process. The most critical disadvantage is that this process is extremely, like I cannot state it enough, extremely moisture sensitive, which is a problem. In fact, the presence of moisture in the reactive environment will block both the initiation of the polymerization and also the propagation of the polymer chains. Our group has been working on the development of polyamide 6 based thermoplastic composites produced by in situ anionic polymerization. We have been focused on the polymerization of neat PA6, and especially we studied the role of the polymerization temperature and the concentration of catalysts on the final properties of the polyamide 6 itself. Then we applied this process to produce different types of composites, for example, basalt fiber reinforced composites, nanocomposites, single polymer composites through the incorporation of polyamide 6 fibers, and also composites containing phase change materials for thermal energy storage applications. For time reasons, I will limit my talk to the description of the neat polyamide 6 and of the properties of polyamide 6 based nanocomposites. We started from commercial products, so we started from a commercial epsilon caprolactam and also commercial activators and initiators that you can see in the slides. So the initiator is a sodium caprolactamate, while the activator is this hexamethylene dicarbamoyl caprolactam, both commercial molecules. The nanofillers that we started from are also commercial nanofillers, both layered nanofillers. The first one is the expanded graphite nanoplatelets, and the second one is the clay, a layered clay, organomodified, so the cloizite 20. They are both layered nanofillers. They have lateral dimensions of some microns and a thickness of some nanometers. This is a scheme of the polymerization setup that we built in our lab. So we have here on the right the reactive mixture, which is mixed all together. So the monomer, the activator, the initiator, and also the nanofillers are mixed here. And then always under inert atmosphere, after the mixture is transferred in the mold, which is already at the polymerization temperature. And here the polymerization happens or is complete in 10 to 20 minutes. We investigated different polymerization temperatures from 145 until 175 degrees C, and also different types of, different concentrations of activator and initiator, which we called low, medium, and high. We explored the whole matrix of possibilities to produce these samples, and so we produced 12 different compositions. After several attempts in which we did not obtain any polyamide 6 because we were underestimating the fact that we have to get rid of all the moisture in the polymerization environment, we actually did manage to produce some polyamide 6 samples. And we started to investigate, first of all, the thermal properties. Here you can see the degree of crystallinity as a function of the mold temperature. And so generally the degree of crystallinity decreases with an increasing with an increasing of the mold temperature. In fact, the increase in of the polymerization temperature leads to higher molecular weight, higher branching, and also higher polymerization speeds. Conversely, a higher concentration of activator and initiator leads to a higher polymerization speed, but a decrease in the molecular weight. We studied the molecular weight also through thermogravimetric analysis, and especially through the DTG curves. We can observe that an increase in the concentration of catalysts shifts the degradation to lower temperature, which we interpreted as a decrease in the molecular weight. Therefore, conversely, the temperature has a very modest effect on these curves, and therefore, the decrease in the degree of crystallinity is especially due to branching at higher temperature and not to an increase in the molecular weight. We actually tried and measured the molecular weight by dissolving our polyamide 6 in a proper solvent. From the literature, we tried, first of all, sulfuric and formic acid. We did not manage to dissolve our polyamide 6. We obtained this nice, full of acid hydrogel, pretty useless. So for sure useless to measure the molecular weight. The TGA also gave us insight on the conversion degree. In fact, we could notice that the conversion degree is very high because we have free monomer in concentrations lower than 1 weight%. Then we investigated the mechanical properties through tensile tests, and here you can see the tensile stress strain curves. Regarding the mechanical properties, we can see that the elastic modulus follows quite well the crystallinity degree, and among all the matrices that we produced, we found that this one, so the 165 L, so 165 polymerized at 165 degrees, and with a low concentration of activator and initiator, was the most suitable to produce nanocomposites. Therefore, we selected this one for the production of the subsequent nanocomposites. These are the SEM micrographs of the cryofracture surface of the produced nanocomposites. Here we can observe considerable aggregation and also limited exfoliation of both the nanocomposite, both the considered nanofillers, which we can appreciate more from these higher magnification SEM pictures. We can observe that the cloisite looks less aggregated and with a higher adhesion with the surrounding matrix. From the DSC curves, we could observe that we have also for the nanocomposites the traditional and expected melting and crystallization peaks. We can observe that the crystallization, if the melting temperature is not very much affected by the presence of nanofillers, the polymerization, the crystallization temperature instead is slightly anticipated with an increase in the nanofiller concentration. We also studied the crystallinity. The crystallinity is already quite high with the neat polyamide 6 sample. Therefore, we could not increase more, or the crystallinity is more or less constant with the addition of both of the selected nanofillers. We also investigated the mechanical properties of the nanocomposites, and as you can see already from these stress strain curves, both nanocomposites lead to a strong embrittlement of our polyamide 6. In fact, we can observe that if the elastic modulus increases with an increase in the concentration of nanofillers, especially this is true with expanded graphite nanoplatelets, unfortunately the tensile strength and the strain at break both drop. In conclusion, we have explored the in situ anionic polymerization of caprolactam, of epsilon caprolactam, for the production of nanocomposites. We for sure will have to work on the dispersion of nanofillers. We are trying some attempts with the sonication of the nanofiller in the reactive mixture and with the addition of polyethylene glycol as the compatibilizers. We are obtaining some promising results. In fact, we can see from here already that the dispersion is quite improving, but we have not investigated the mechanical properties yet. For the future, we would like to explore this reactive processing of polyamide 6 with renewable fillers and nanofillers. In fact, this processing is very promising because it's very low processing temperature, no? Maximum 170, 175. And therefore, I would like to try with, for example, flex technical textiles. However, since we all know that these kind of fillers and nanofillers have very high amount of hydroxyl groups on their surface, this is not acceptable for our polymerization of caprolactam. Therefore, we are studying, or we are looking for proper surface treatment. So if any one of you has an idea of which surface treatment can be suitable for these fillers, please let me know. Thank you very much for your attention.
Thanks, Julia, for the nice talk. So, time for questions. Over there.
Hi, thank you for a nice presentation. My question is, when you change the different parameters of the synthesis, like the temperature and the percentage of initiator, do you think there is one of the samples that stands beyond the other, or do you think the synthesis is quite versatile and tolerates a small variation?
So regarding the conversion degree, we obtained a very high conversion degree, so a very low concentration of free monomer at the end for all the selected compositions, once the process is properly shielded from the moisture environment. About the mechanical properties, actually, we noticed that a low concentration of activator and initiator and intermediate temperature give materials with better strain at break, especially. The crystallinity is more or less there, but the strain at break is really affected by the combination of these two parameters.
Okay, thank you.
Over there.
Hi, thanks for your presentation. I was curious about the gel formation you obtain in the solvent. I've understood that it was an unexpected behavior, so I was wondering if you have an explanation for this behavior, and if this can open to other application of for your polymer.
So linear polyamide 6 should dissolve in formic acid and sulfuric acid. Since we did not dissolve it, we think that it's or very highly branched or also cross-linked in at least to some extent. This is actually quite interesting because it will increase or improve the properties in temperature of this polyamide 6 if it's slightly cross-linked. We have not investigated it yet, but we are quite confident that if it is cross-linked, then it will withstand better, or the properties in temperature will be better. We have tried to substitute this formic acid and sulfuric acid with other solvents that can be put in a CO2, a supercritical CO2 environment in order to create a sort of aerosol out of this, but we have not succeeded yet. Until now, we have not found any other solvents except formic acid and sulfuric acid, which should dissolve these polymers, to produce this kind of structure over here. Okay. So not yet, but we tried this and we did not succeed in making anything out of this yet. Okay. But
thank you.
Other questions?
Thanks for your presentation. I would like to ask you if you would recommend such an approach to produce manufacts with good aesthetic properties, because I guess that say the low processing temperatures can prevent the degradation of the fillers and the fibers especially that you use. What do you think?
Yes, I think that the fact that this process is performed at a lower temperature, it will be suitable for the incorporation of thermally sensitive fillers, such as the natural fillers. I did not get which property.
Aesthetics.
Like the surface finishing.
Correct.
Yeah, it could be, yes. We have not investigated it yet. We are trying and produce some samples which are good enough for the mechanical tests for now. We are not focusing our attention on the surface finishing, but it could be also because the reactive mixture is very, the viscosity of the reactive mixture is very low. So it can really go everywhere if you let it. The viscosity is like that of water, more or less, some units of Pascal per second.
Thank you.
So let's thank again Giulia. And now the talk. And I have to go.
Sì, no, più che condividere sarà solo lo schermo, da vedere questo schermo. No, non condivide, non penso che faccia una Vediamo il microfono, proviamo il microfono. Sì, è attivato. Ci sentite? Ci sentite? Dovrebbe essere già a posto. Ok. Vediamo, sì. Sì, il nostro è questo, anche loro. Eccoci. Bene, cambio un attimo in italiano. Per presentarvi a chi non lo conosce, per rivedere il professor Pedemonte. È un grande piacere condividere con lui in questo momento. Il professor Pedemonte è uno dei firmatari nel 1975 dell'associazione AIM, poi presidente della scuola che è stata fatta per anni a Garniano, ora a Bertinoro, quindi la scuola dedicata poi a Mario Farina. E in corrispondenza, come si è detto il primo giorno, in corrispondenza di quelle scuole è stato proprio istituito Macrogiovani nel 98, no? Quindi il 25esimo oggi. E il professor Pedemonte è stato uno dei sostenitori convinti di questa attività, di questa iniziativa. Abbiamo sempre avuto piacere di condividere con lui questi momenti di discussione scientifica e di piacevoli momenti conviviali, e quindi anche comunque questo saluto ci fa molto piacere. E quindi passo la parola a Enrico, che posso chiamare Enrico perché oltre a essere il professor Pedemonte con i ruoli che ho appena ricordato è anche il mio professore. E quindi con grande affetto passo la parola al professor Pedemonte.
Grazie Silvia della presentazione che mi imbarazza un po', ma via. Ti ringrazio. In effetti io sono stato attivo nell'associazione dalla sua fondazione, sono stato attivo per 30 anni e scoprendo diversi ruoli, tra i quali quello di direttore della scuola di Garniano. Allora, di rendere Macrogiovani indipendente dalla scuola di Gragnano e soprattutto itinerante, in modo che potesse essere fatto al nord, al centro e al sud. E questo è quello che oggi abbiamo di fronte. Che dire? Certamente Macrogiovani è stata un'idea molto interessante che altre associazioni o gruppi di studio in Italia cercarono di copiarci e di sottrarci con metodi, mi permetto di definire scorretti, perché i giovani relatori venivano retribuiti. Quindi noi siamo ancora vivi, loro non ci sono più. E questo va a merito dei giovani dell'AIM che danno sempre una risposta entusiastica alla nostra iniziativa. Vorrei concludere questa mia breve presentazione perché so che avete il coffee break e non voglio sottrarvi del tempo a un momento di socializzazione. Vorrei ricordare che il merito di Macrogiovani non è soltanto mio, è merito del direttivo di allora. Presidente era il dottor Albizzati della Pirelli Cavi. Mi aiutò molto nella realizzazione del primo evento Loris Giorgini dell'Università di Bologna, attualmente professore all'Università di Bologna, ma voglio ricordare, concludendo, che l'idea prima di un qualche cosa per i giovani è venuta all'associazione e al sottoscritto che l'ha sposata con entusiasmo da alcuni giovani dell'Università di Salerno. Capofila, e penso che sia tra di voi se non sono male informato, è la Giuliana Gorrasi, a cui va il nostro ringraziamento.
È qua con me. Eccola. È qua con me.
Eccola.
Grazie a te.
Giriamo un attimo la telecamera così abbiamo piacere di salutarti. un attimo, ma ce la facciamo. Ecco. Bene, ti ringraziamo davvero tanto, è stato veramente un momento davvero piacevole. E noi ci rivediamo a casa e quindi a prestissimo. Ecco sì, come giustamente il professore ha detto, adesso è il momento conviviale del coffee break. Grazie, benissimo.
Mi ha glielo devo dire, era imbarazzata perché non è giovane come 25 anni. Grazie.
Vabbè, posso fare io? Allora, la prima.
Beh, che in realtà io sono la prima.
Non è importante.
Perché non solo sono in categoria, ma ognuno con la
E la prima?
Macrogiovani, sì.
Perfetto.
Un viterio per la presentazione.
Quindi tu chiedi a Pedino. Ora ci diamo. Un secondo solo, ok. Sì, no, prima ci disattiviamo dai monitor.
Altrimenti spoiler.
Esatto. Ok, ora possiamo andare in presentazione. Anche se lui forse mi riaggancia. Sì, infatti. No, io la tolgo. E solo devo fare 2 volte, devo convincerlo che non vogliamo i monitor.
Va bene, perfetto. Ok, stupendo. Niente, la pelota con la scrivo solo con la voce.
A me? USB, questa non ce l'ho. Sì, ce l'ho, non ce l'ho. Vediamo se è vero. Vediamo. Macrogiovani FRV2 oppure presentazione Macrogiovani C?
No,
FR, ok. Certo. Siamo sganciati dai mono, quindi la possiamo anche mandare in. Sì, però ci dobbiamo ridire che non vogliamo. Ok, siamo isolati. Se vado veloce me lo dici, eh?
No, giusto per controllare che fosse tutto insieme. Perfetto, grazie.
Si figura. Il pennino. Dopo che abbiamo fatto tanto per farlo funzionare.
Io il giorno non è mio tanto.
E dai, quindi.
Sei perfetto che me lo sai dire.
Allora, scusi. L'ho segnato Francesca, vero? Sì, perché come siete due uomini e due donne, quindi l'unica donna che me ne è rimasta era lei. E infatti è FR Francesca. Vedete? 11:40. Così mettiamo in ordine di scaletta. Ok, lei Zago Stefano Macrogiovani.
Dovrebbe essere
Sì, esatto. Ed è alle 12:15. Tutti su 12, anche lei vuole vederlo?
Sì.
Ok.
Perché non bastano 200 volte questo il mio
Sì. No. Tanto non c'è no, io come, però come gli altri giustamente, lui deve fare quello che dico io.
sono un po' di animazioni che dicevo, quando solo su questo si vede il cambio colore,
Sì.
ok, io vedo un cambio di colore.
Sì.
Perfetto.
Un cambio soltanto ha fatto? Un cambio
Sì,
solo?
Sì, uno solo.
Ok,
Basta
perché
vedere
se
il
poi
rosso.
possiamo, se vuole...
No, va benissimo così. Perfetto. Cioè, peccato un sacco ieri per tastare sto video perché partia sempre nel momento sbagliato. Questo.
Ah sì, scusi. Sì, sì, questo
Sì,
con la goccia che sta cadendo sopra siamo a posto e si espande con la rotazione. Chiudiamo e possiamo togliere. Allora, sì.
Mi dai il permesso? Allora, però io ovviamente... 11:30.
Oh, okay, I think we can start. So welcome back to this last session of the 25th edition of Macrogiovani. I'm Martina Martuscella, I will be the chair lady of this session. I think that we can move on with postdoc's presentation with Angelo Nicosia, that will speak us about his work on an antibacterial agent based on polymer graphene derivative decorated with silver nanoparticles. Angelo, the stage is yours.
Okay, thank you for the presentation and good morning to everyone. Okay, so I'm here again talking, but now in English and about science. So today I would like to talk about this project, which is a project to which I am mostly attached. It was developed during my PhD research and is related to the development of a polymer-based antibacterial agent. But why a polymer-based antibacterial agent? Because all of us love polymers, of course, but especially because polymers are used as structural materials for a lot of objects, going from kids' toys to biomedical devices such as catheters, ureteral stents, and all of these materials are subjected to the bacterial attack. And this is a huge issue, especially if we look at the biomedical devices. So, to avoid this kind of risk, I would say, during the history have been used these low-weight organic molecules, such like this, which ensures the long-term antibacterial properties on the surface of the polymer-based materials. The use of these molecules is really ubiquitous, I would say. Indeed, these are not only used as coating, but are only used in personal care products like toothpastes and also creams that we use for our body, and textiles, reaching a market of about $900 million in 2015. But this market also grew during the COVID-19 pandemic. But what is the relation between antibacterial agents and viruses? It's strange, but they are different, but the relation is due to the life of the bacteria. Indeed, after the bacterial adhesion on a surface, it comes in succession, the colonies, proliferation, and then the formation of the biofilm, which is a secretion of the bacterial cells that protect the bacteria from the environmental stresses. And this biofilm is also exploited by viruses as a shield from the environment, but the most important thing is that they exploit it also as a spreading way. And during the pandemic, we all became aware about the dangerousness of touching the common and contacted surfaces. So, going back to the low-weight organic molecules, these molecules suffer of low adhesiveness on the substrates, and these results in their environmental release and spreading. The presence of these low-weight organic molecules in the environment results in bioaccumulation within organisms. These molecules are endocrine disruptors, so they lead to asthma, allergies, and other strange stuff, such as body malformation. And last but not least, these molecules train the bacteria for the multi-drug resistance, making every day more difficult to fight bacteria. For all of these reasons, the governmental agencies such as FDA, but also in Europe, we are starting to do something, altered to the use of this kind of molecules in the common products. So there is the need to find an alternative. An alternative can come from the nanomaterials. So we all know that silver nanoparticles are already famous for their antibacterial activity. They are a widespread antibacterial agent acting against gram-negative bacteria, gram-positive bacteria. But recently, also graphene oxide have shown its properties as antibacterial because of its mechanical stress on the bacterial cells. And very recently, the mixture of the two shown interesting antibacterial properties. But there is still the issue of the adhesiveness on the substrate. So here comes my project, a nanotechnology-based approach to develop an antibacterial agent, mixing the properties of graphene oxide and silver nanoparticles with the properties of the polymers that are the keystone of this project, that ensures the adhesiveness on the substrate and lead to the long-term stability of the antibacterial agent. And we call this system nanohybrid graphene polymer silver more friendly nano-high GPS. The synthesis of this system is really simple. It's a two-step procedure. I will show you the procedure briefly. So as a model, we started with polyvinyl alcohol because of the hydroxyl group present. And in a mixture with graphene oxide was performed a catalyzed esterification reaction. The occurrence of the ester bond was verified through NMR spectroscopy. Revealing the esterification reaction. And then, moving to the second step, it was mixed the polymer derivative of graphene oxide with silver nitrate in an aqueous solution, and with the 2 minutes reaction, very quick and without any reduction agent. It was performed contemporarily, the reduction of the silver nanoparticles and of the graphene oxide platform to reduced graphene oxide. Using different amount of silver nitrate, we produced a free compound having a different content of silver nanoparticles. The reaction condition was also applied to the bare materials, so graphene oxide and also the polymer-based derivative, to understand what occurs on onto the carbon platform, revealing that the reduction of the graphene oxide occurs with the shift to the new band at 266 nanometers, and also the changing of the slope of the polymer derivative after the reaction confirmed the reduction of the platform. Going to the silver nanoparticles instead, we can see that the plasmonic signal of the silver nanoparticles is really similar to the one of this one, which are common silver nanoparticles synthesized through the sodium borohydride reduction of silver nitrate. The only difference is here in the full width half maximum of the band, just because of the interaction between silver nanoparticles and the substrate of graphene oxide. The content of silver nanoparticles of each nanosystem was verified through thermogravimetrical analysis in air atmosphere, and then we moved to morphological analysis with the SEM-EDX analysis, where reducing the content of silver nanoparticles, we can see the increasing homogeneity of the nanosystem, where in the sample number 1, we struggle to find nanoparticles, but these are present. Just look at the EDX analysis. Anyway, for this reason, this sample was the one chosen to go in depth with the microscopy analysis. So the AFM technique revealed that the silver nanoparticles are homogeneously distributed not only onto the graphene oxide platform, but also here in the polymer-based region, confirming that the silver nanoparticles nucleate onto the defects of the graphene oxide, but also exploiting the hydroxy group of the polyvinyl alcohol. And then the high-resolution TEM technique confirmed the same instance with the presence of these silver nanoparticles within this polymer matrix. Finally, we performed a functional characterization. So we decided to focus onto the common bacterial population of common and contacted surfaces, such as keyboards and doors handles. This bacterial population was recovered through a cotton's web onto the keyboards, and then the bacteria population were counted with the plate count agar method. The experiment revealed that in the control we can see a lot of nice spots with different colors revealing the plethora of bacterial species present on these surfaces, but in the applying the nano-high GPS, the one with the highest content of silver nanoparticles, not aggregated, it revealed the 94% of reduction of bacterial species. And also the system was more efficient than silver nanoparticles themselves, and also more efficient than silver nitrates. In conclusion, the system is potentially versatile because depending on the substrate that you want to treat, you can change any polymer having OH groups or amide groups or amine groups useful to perform esterification or amidation reaction. And from an industrial point of view, it is really, really interesting because you can apply it onto already produced object through economic techniques such as spraying, dipping, brushing, or you can also mix it in the productive chain of a new object by mixing it directly with the polymer matrix using the right polymer. I would like to thank all the researchers that supported me during the development of this project. And of course, the laboratory of which I am a member, the Polymer Laboratory of the Department of Chemical Science, and especially the head of the laboratory, the Professor Mineo, here present, which is my mentor, that support me every time. And before leaving the stage, I would like to promote something. So this is the last editorial project of the laboratory, the special issue on nanomaterials for potential uses in extraterrestrial environments. Feel free to ask me everything during the light lunch. And finally, thank you all for being here in Sicily, and it has been a pleasure to host you here.
Thank you, Angelo, for your nice presentation. Are there any questions for him? Okay, there's one. There's two questions already.
Hi, thanks for your presentation. I would like to ask if you are interested also into direct food contact, and in case the safety of this technique. Direct food contact.
I did not understand.
Direct food contact.
Direct food contact.
Yes.
Yes, of course.
And the safety of this.
We are not, so I would say the aim of this project was not to use these onto materials to be in contact with food, but this is a thing that we could think about. It could be a little bit strange because usually with food you mean the package, the top, yes, right? Like cellophane and this kind of stuff. Okay, it is interesting, but now we are focusing on to the common bacteria population. The next experiment that we are going to do are with controlled bacterial population, just to see really the efficiency, because this is really a proof of concept experiment. So we are not so in depth into that stuff.
Perfect, thank you.
Thank you for the question.
Thanks, Angelo, for your talks. Silver metal typically is characterized to an oxidation, easily oxidized to form silver oxide. Have you checked the oxidation state of your metal nanoparticles?
The oxidation state of the...
You have a mixture of metal one and the silver oxide.
Okay, no.
Have you checked by XPS analysis, for example?
No,
No.
we didn't perform it, but just because we had a lot of struggle with XPS. We tried, but since the concentration of the silver nanoparticles is really low, the XPS struggle a lot to find it. So we saw the nanoparticles with the thermogravimetrical analysis, and we don't see nanoparticles with the XPS. We are working on that with a team here of the department, so I will give you some updates in the next future.
Perfect, thanks, Angelo.
Other questions? Okay.
Thanks for the presentation. I have just a curiosity. Have you evaluated the use of other silver nanoparticles with different shapes, like pyramidal or?
Okay, nice question. I can't right now. I thought on that, but I can't because of the reduction procedure. Because since it's microwave assisted, you can't control so much the shape of the nanoparticles. So it's just, yeah, it's quick, it's nice, you just use aqueous solution, no reactants, but you can't control morphology. So it's about pros and cons, you know. And, but I can try with another procedure, and that's a nice idea. Thank you.
Okay, let's thank again Angelo. And let's continue with the second presentation of this session, held by Francesca Ramacciotti from the University of Bologna, with her work on composite electrospan mats as sustainable photothermal system for artwork restoration. Okay, Francesca, the stage is yours.
Thank you. So, good morning to everyone. Today I will present you the first results related to the production and characterization of composite electrospan mats employed as sustainable photothermal system for artwork restoration. So, restoration process is a very complex one and composed of different procedures, and one of the most important and delicate ones is the cleaning, which is irreversible. Indeed, the range of materials that have to be removed from artwork surfaces is very broad, and it goes from simple dust to polymeric coatings, such as natural or synthetic varnishes applied by the artists themselves, or conservator restorers, but also vandalic acts. These polymeric coatings represent a great issue for conservator restorers as they degrade over time and become highly insoluble. Why solubility is a problem? Because traditional cleaning systems rely on the use of cotton swabs coupled with organic solvents rolled on the surface. These traditional systems present the major drawback associated with the scarce control exerted over the release of the solvent. So the solvent may interact not only with the layer to be removed, but also with the one to be preserved. This interaction may further endanger the artwork, so in terms, for example, of redistribution of soluble components, swelling, embrittlement, or mechanical damages. Therefore, research is focusing on the development of new cleaning systems which are highly retentive for the solvent and then less invasive toward the artwork, but also taking in consideration sustainability and non-toxicity, especially considering the health of the operator, which is exposed to the organic solvents. So, electrospinning is a technology that exploits electrical forces to produce polymeric materials in form of non-woven textiles, which present sorbent abilities, and it is a technology very versatile that has found a broad range of application in technological fields, and recently also in the one of conservation and restoration. And indeed we have patented the use of electrospan mats coupled with organic solvents for the peel-off of triterpene varnishes from painting surfaces. So the aim of this work is to further implement this system, taking into account the highly insoluble layers. So we want to exploit a local temperature increase to enable a better removal of, for example, reticulated alkyd paints. So in this work I will present you the production of these materials with photothermal agents, the study of their morphology and their thermal behavior, and I will present you their first application coupled with the gamma valerolactone, which is a greener solvent and non-toxic, for the removal of alkyd spray paints from marble surfaces. So, as photothermal agent, we have selected melanins, which are a class of dyes present not only in the human body, but also in animals, for example, in the ink of squids. Melanins are photothermal agents as they absorb in the UV visible range, and they have a non-radiative relaxation, which results in an increase of temperature. So, we have used a dispersion of nanoparticles of melanin obtained by the purification of squid ink in water, in which we have dissolved pullulan, which is a bio-based polysaccharide. This solution has been then spun with the electrospinning technique to obtain mats with a thickness ranging between 300 up to 400 micrometers of thickness. Then the materials as produced have been characterized and then tested. So, coming to the morphology, we obtained BIBS-free fibers, which display an average fiber diameter of 0.37 microns, and as you can see from the TEM micrograph, the nanoparticles are inside the pullulan fibers. We have assessed also the concentration of nanoparticles inside our mats, and we have seen that the value that experimentally we have obtained is very close to the theoretical one, meaning that we didn't lose any particle during the process. So coming to the photothermal properties, the first thing that we wanted to assess was the temperature increase by varying the LED intensity, which has been varied by increasing the electrical current. As you can see, and as we expected, with low currents, we have a low temperature increase. For example, with a 0.1 ampere current, we have just 10 Celsius degrees increase, while going up with the current, for example, with a 0.5 ampere current, we have reached almost an increase of 90 Celsius degrees. Then we wanted to assess the stability of our mat upon cycles of irradiations. And as you can see, after 5 irradiation cycles, the maximum temperature reached by our mat is not varying, not only with low LED intensities, but also with high LED intensities, meaning that our mats are stable. Last but not least, for also application purposes, we wanted to evaluate the relationship between the maximum temperature reached by the irradiated surface, which is the one that we are monitoring, and the phase that is not irradiated, because it will be the one in contact with our cultural heritage. So temperature is important because of conservation issues related to the delicacy of the object. And as you can see, we found a linear correlation between the maximum temperature reached by the front and the maximum temperature reached by the back. This correlation is very helpful during conservation procedures, as we can predict or adapt our cleaning to the needs of the object. Coming to the test, so the cleaning, the first cleaning test, we have prepared a standard sample. We, of course, didn't test our mats on a real cultural heritage. And these standard samples are prepared by spraying Montana Color Alkyd spray paint on a marble slab. We have selected the Montana Color spray paint because it is very diffused, not only among artists, but also among vandals. Then we have let our sample at room temperature for 1 month in order to give the time to the spray paint to stabilize and fully reticulate, so to achieve the situation where it is highly insoluble. And as you can see, we have a paint thickness of around 16 microns. Then we have tested our mats coupled with gamma valerolactone that, as I said, is very non-toxic and sustainable. And as you can see, after 1 minute of application, if we don't increase the temperature, so we don't use any irradiation, the surface of our object is almost intact, so we don't have any damages to the paint layer. While if we irradiate and thus increase the local temperature, as you can see, we achieved almost complete removal of the paint layer. So meaning that our cleaning process was successful. So in conclusion, with the electrospinning techniques, we were able to produce a completely green composite material because we used melanins obtained from squid ink, pullulan, which is a bio-based sugar, and water as solvent for our spinning solution. So it is a starting material completely non-toxic and environmentally friendly. In addition, the solvent that we have selected is considered a greener alternative, and it is not toxic. Coming to the photothermal behavior of our produced mats, it is stable upon cycles of irradiation, and we have a linear correlation between the temperatures reached by the irradiated side and the non-irradiated side. Finally, coming to the application and the purpose of this mat, we had the promising results in the removal of spray paint from marble slabs. In perspectives, we want to evaluate even other production processes for obtaining photothermal composites. We will evaluate their photothermal behavior, and we will evaluate the photothermal behavior of the materials also in wet conditions, which are actually the ones in which a conservator restorer will find himself or herself. Finally, the mats will be tested not only to remove spray paint from marble, but also to remove spray paint from mural paintings, which are realized with similar materials. So we will complicate even more the cleaning situation. And then we will also test these mats on degraded natural coatings that are usually found on paintings. So I want to thank the organizing committee, my lab group, and all the other laboratories that have participated in this research, and you for your attention.
Thank you, Francesca, for your very interesting work. Does someone have questions? I have some curiosities for you. I would like to ask you if how do you apply the mat on the surface of the marble? For example, you just touch it?
You put the solvent on the mat, then you transfer it on the surface. You apply a little bit of pressure to ensure adhesion between your mat and the surface. Then you wait 1 minute or even more, and then you remove it. In the case of marble, you need anyway a cotton swab to remove the residues of spray paint. In the case, for example, of natural varnishes, you don't need cotton swab, but the varnish is completely absorbed by the mat, so you just peel off your mat and you have a cleaned area.
Okay, and there's possibility to remove the varnish from the mat after, so to reuse the same mat?
the reusability is something that we will work on once we have optimized system, but in the case of spray paint, we don't have any residues of spray on the mat, so it can be reused. In the case of natural varnishes, it's more complex because it is inside the pores.
Okay, thank you. Okay, let's continue with Cecilia Velino from the University of Bologna with her talk about, development of a novel hyaluronic acid hydrogel system for enhanced loading and controlled release of active molecules. Thank you, Francesca, and the stage is yours. Sorry.
Okay. All right, so good morning, everyone. Thanks for being here, especially after yesterday's social dinner. I know it's been challenging to be here this time. So my name is Cecilia, and I am the latest acquisition of the Polymer Science and Biomaterials group of the University of Bologna. And as the attention threshold decreases during the time, especially today, I'm going soft with a presentation on my latest research on the development of a novel hyaluronic acid hydrogel system for enhanced loading and control release of active molecules. This research is a part of a bigger project which is financed by the Ministry of Health and carried out in collaboration with the chemistry department of the University of Bologna and the Ramses laboratories of the Orthopedic Institute Rizzoli of Bologna. The main aim of the project is to develop personalized strategies for the treatment of osteoarthritis. So, what is osteoarthritis? As you might know, it is a prevalent joint disease which affects millions of people worldwide, so it's a quite common condition, which is clinically characterized by joint pain and joint instability. It is frequently found in hip, knee, and intervertebral joints, and the most applied current treatments for this disease are mainly consist of local treatments by intra-articular injection of viscosupplementation materials and active molecules. But the main drawbacks of these local treatments is that their short-term action involves frequent local injections, which is not the most suitable conditions for patients, of course. Among the most used materials for this purpose, there is that have been used for the treatment of osteoarthritis. There is the hyaluronic acid, as you might know, as it is a natural polysaccharide which is found throughout the body, and it's a key component of a synovial joint fluid, which is the fluid that reduces the frictions when you do a movement. Because of its chemical and mechanical properties, this hyaluronic acid has been widely used in a variety of biomedical and clinical applications. But the main problem related to these materials is it that being water soluble, it is quickly degraded in vivo by enzymatic or hydrolytic reactions. So the most common solution to this problem is to chemically modify hyaluronic acid by cross-linking it, and this process leads to the formation of an hydrogel that, as we all know, is a three-dimensional polymeric material, which is a solid, but it can absorb a large amount of water, up to 90% of its weight. But even after the chemical modification of hyaluronic acid and the formation of the hydrogel, we still face some problems related to the material. And those problems are mainly related to these two factors, which are the uncontrolled and fast release of active molecules and problems related to injectability. Both these parameters are in fact directly related to what it is the cross-linking degree of the material. In fact, as we increase the cross-linking degree, we reach a better drug retention, which guarantees a slower release of active molecules we can put inside the material. But increasing the viscosity gives birth to problems related to injectability of the material. So the aim of this study was to try to overcome these limitations related to the hydrogel, hyaluronic acid hydrogel, by developing a novel system based on hyaluronic acid hydrogels that would be able to enhance the active molecules loading and release, but maintaining a good injectability. To do so, we thought about building this kind of novel system, which is composed of a dispersion of the cross-link hyaluronic acid microparticles in a non-cross-link hyaluronic acid solution. So as you can see from the scheme here, we have from one side the hyaluronic acid solution non-cross-link, which guarantees low viscosity of the overall system, and from the other side we have the cross-link hyaluronic particles, which can be loaded with active molecules. These two components are then ideally mixed together, injected in the articulate site, and then here we can assist to the in situ release in the site. So the first part of the development of this material was to cross-link the hyaluronic acid. In this phase of the study, we decided to take it easy a little bit, so not to complicate stuff. And we decided to use a really commonly used cross-linking agent, which is the butanediol diglycyl ether, also known as BDDE, because it's a really commonly used cross-linking agent for hyaluronic acid, so the literature is really vast in this sense. The reaction of the cross-linking is really easy in mild conditions, so it was really easy to cross-link, to obtain the cross-linking. And after the cross-linking strategy, we had to obtain the particles. And in this case, we decided to explore two different approaches. The first one was obtaining the particles by mechanical crushing of a bulk material with an homogenizer. And the second strategy was to obtain the particles directly during the cross-linking reactions using a water in oil emulsion. Both the particles we obtained with these two methods were characterized and through optical and electronic microscopy. And as for the crushed particles, as you can see from the images, we obtained some materials which were really heterogeneous in both shape and morphology and size. We were able also to determine by NMR the cross-linking degree, which was found to be around 70%. And better results were obtained when we characterized the particles obtained by the emulsion strategy. In this case, as you can see from the slides, we were able to obtain almost perfectly spherical materials, and this result was confirmed by optical microscopy and electronic microscopy. And moreover, we decided to test and to evaluate the efficiency of the formation of the hydrogel by putting in contact the dry particles with water. And as we were able to see from the optical microscope in a live movie, which is not possible to reproduce here, once the dry particles is put in contact with water, it starts absorbing water and swelling, but always maintaining its original spherical shape, which was a really nice result. After the preparation of the particles, we had to build our dispersion system, so we had to disperse the particles in a non-cross-link hyaluronic acid solution. We decided to try a few concentrations to start, as we wanted to obtain a system which showed some mechanical and rheological features, such as a gel-like behavior, suitable viscosity values, of course, related to the injectability of the system, shear thinning behavior, and appropriate particles concentration, important for the drug loading and release. All the systems and the concentration we tested were characterized through rheology in order to determine the storage modulus, the loss modulus, and the viscosity of the system. And so the first test we carried out was an amplitude sweep test in order to determine the two moduluses and to evaluate the behavior of our materials. Compared to the non-cross-link hyaluronic acid solution, which of course exhibit a liquid-like behavior in which the loss modulus is higher than the storage modulus. And as you can see from these graphs, is that for both the particles and in a different concentration for all the system, we obtain a gel-like system. Another parameter we wanted to assess was, of course, the viscosity, which was a key parameter to determine. And even in this case, for both crushed and oil obtained particles, we see that with respect to the non-cross-linked solution, we have an increase of the viscosity of the system, predictably. But especially for oil, we can see that this difference, so the black line with respect to the red and the blue line, are not so different. And these results, which is promising by itself and really interesting, was even better when we compared the numerical values of the viscosity with a characterization we performed on a commercial hyaluronic acid formulation, which is provided by Fidia Pharmaceuticals, as his name is Yalubrix, which has been already used in this kind of application. This commercial formulation exhibit a liquid-like behavior, and if we compare at the determined shear rates the viscosity of the commercial formulation to the one we obtain with our system, we can see that we are almost in the same range, and this is especially true for the oil-obtained particles. So really promising results. So, in conclusion, we were able to develop and characterize the cross-linked hyaluronic acid hydrogels microparticles, which were then dispersed in a non-cross-linked solution of hyaluronic acid in order to obtain this novel system. Of course, the system itself needs to be optimized in the further studies in order to obtain materials with the desired and optimal properties, depending on the purpose. The next step will be, of course, the evaluation of the drug loading and release of the system, which is a key parameter as well, and something which will be done in the next days, the cytotoxicity assessment, of course, on the cells. So I would like to thank the Polymer Science and Biomaterial Group, coordinated by Professor Maria Letizia Focarete, my tutor, Professor Chiara Gualandi, who welcomed me a few months ago in their lab, and of course all my colleagues and friends which are here today. And thank you for your attention. Thank you very much.
Thank you, Cecilia, for your very interesting presentation. Are there any questions? Okay, I have a curiosity for you. You have a target of viscosity, so on rheological properties that you want to get.
Okay, so far the target was to obtain viscosity which were comparable or below the one we have for commercial gels. Because we already have, like, hyaluronic acid hydrogels are widely used for intraarticular injection, but their problem is mainly related to the high viscosity of this material. So once I reported the results we obtained, which are lower a little bit, we of course need to carry out some more tests, they were really satisfied that the less is the viscosity, the better for the system to be injectable. So we don't have a target, but we cannot be over. It cannot be higher than the commercial ones, of course.
Okay, and I wanted also to ask you about the drugs that you want to release. You have already think about some drugs to start with.
Okay, yes. So the project, which is called Nutperoa, it has as a target materials some nutraceuticals, which have been found to be active as inflammatory activity towards the osteoarthritis sites, which is, of course, prone to inflammation. So we will go with those kind of nutraceuticals for now.
Okay, let's thank again Cecilia. Okay, we can move on with the last presentation of today and of this Macrogiovani. And welcome to Stefano Zago from the University of Genoa with his work on polymer-based photonic sensors for the detection of toluene in water. Stefano, the stage is yours.
Thank you, Martina, and thank you all for being here. My name is Stefano Zago, and I work at the University of Genoa, and I'm going to present you today the polymer-based photonic sensor for detection of toluene in water. This image briefly sums my work, which basically use the same principle that colors the wing of a butterfly to detect the presence of pollutants in water. This is all part of a PNR project named RAISE, which stands for Robots, and IE for Economic Empowerment. Basically, this is a project aimed to make an ecosystem of innovation for the improvement of quality of life and social and economic. Basically, the project is focused on robots, but we work in Spoke 3. There's something wrong with this? Okay. We work with Spoke 3, which is aimed to development of robotic system for environmental caring. Therefore, our group works with a sensor for detection of pollutants into water. Now, let's present some of polluting molecules. As we know, nowadays there are a lot of pollutants. This is just a minor part, focusing on organic pollutants, lots of different molecules, and we will focus into two of the more widespread and interesting polluting molecules, so PAH and VOC. VOC stands for volatile organic compounds, and PAH stands for polycyclic aromatic hydrocarbons. These molecules are quite dangerous, not only for as humans, but also for animals. And as you know, because of the food chains, we can assimilate molecules that has been assimilated by other organisms like fish. Like yesterday, we ate a lot of fish, so we hope there were no volatile organic compounds inside of that. And we have to choose a molecule to model these pollutants, and our choice is toluene, because it's a molecule which is part of the. This is better? Okay. Sorry. So, it's part of the volatile organic compounds, technically, but shares some similarities to polycyclic aromatic hydrocarbons because of the aromatic structure and similar polarities. Therefore, this is our model molecule for this study. Traditional sensing in water is carried on by lab analysis, meaning that we need sampling, pretreatment, and further analysis. This is good, but needs workers for the analysis, time, and complicated equipment that not all laboratories can have. Nowadays, the more modern approach to sensing is in situ analysis, possibly automated analysis to make that quick and effective. Our solution is the photonic crystals, because these are a spectroscopic analysis that make use of the change of color of these structures, meaning that we have a quick and effective detection of pollutants. I hope you can see in this video the change of colors from green to red after exposure to toluene vapor. This has been used in our laboratory for vapor detection, but water detection is more difficult because of different phenomena such as solubility and volatility of the species. Therefore, this is a new challenge for us, and we want to see how photonic crystals behave. What is photonic crystals? Well, yesterday Martina gave you a brief introduction, so I will just freshen your memory. They are ordered periodic structure made by materials with different refractive index, meaning that the periodicity can be in 1 dimension, 2 dimension, or 3 dimension, and this type of structure is quite common in nature, like the wings of the moth butterfly, the peacock wing, the peacock feathers, and the exoskeleton of some bugs. They are all photonic structures, and this is color from structural color, not from pigmentation or dyes. These materials, without the photonic structure, will be transparent. Now, the most simple photonic crystals are diffracted Bragg reflectors, meaning the periodicity is just in one dimension. So it's a stack of different layers. And at the interface happens a lot of phenomena that are refraction, reflection, and transmittance. This gives rise to a lot of different interference, but we can exploit the periodicity of the system and see only a selected wavelength with the enhanced reflection. And this selected wavelength is called photonic band gap. We can also call it reflection peak, and is described by the Bragg-Snell law. The parameters affecting this peak are the thickness of the layers, which is the D, the different refractive index, actually the effective refractive index, which is a volumetric average, and the angle of incidence. Luckily, in this presentation, I will not change the angle of incidence, neither I will change the diffraction index, meaning I will not change the materials. So we can only focus on the D, which is the thickness. Now, yesterday Martina showed you that the mechanical stress can produce a variation. What also can produce a variation? Well, imagine we have a molecule like toluene interacting with our DBR, which is a stack of different layers. What can happen is that one kind of layer, or actually even both of them, can swell, meaning there is a difference in thickness and a shift in the signal. And for our materials, our choice has been polystyrene and cellulose acetate. These are their refractive index. And they were casted on a glass substrate by the process of spin coating, which is very easy and reproducible. It starts with the deposition, the thinning. We make that dry and become solid. Then we repeat the procedure in order to obtain a different multitude of layers that can increase the signal in reflectance. Now, let's see what actually is the response in polluted water by toluene. Well, we already saw that there is a shift in the peak, and this was actually the results of our measure. But I can show you more. This is a contour plot, meaning that we observe the time evolution of the peak variation. Basically, imagine to watch the spectrum from above, and you see the red is the high reflectance zone, the green is the low reflectance zone. It's like watching the map of a mountain, for example. And basically, you observe the variation over time. So we have a very fast shift in order of minutes, and then it shifts back into blue. This is the behavior in saturated toluene solution. So as I told you, there is a solubility and volatility phenomenon occurring. For lower concentration of toluene, we don't have the shift back, but we only have the initial red shift quite fast in the order of minutes. Because of this different behavior, we wanted to investigate the role of concentration by performing a calibration. So with 5 different concentrations, we observe different kind of behavior and different variation for the reflectance peak. And to make order in these plots, we decided 2 times 2 as a control time, and we plot the difference of lambda compared to the concentration in order to observe if there is a trend. Fact is, there is the trend. Basically, we don't have a model yet for this, but this is the starting point for quantitative analysis from these sensors. Therefore, what are the conclusions? Well, we have obtained from very simple polymers, which are polystyrene and cellulose acetate, an effective sensor for toluene. And we also observe a correlation between the optic response and the concentration, meaning that there is a margin for quantitative analysis. What are the future perspectives? Well, for now, we chose only one molecule. We can try other molecules, but more interesting, we want to test with mixtures and eventually go with real seawater in order to observe the behavior in such complex system. Also, we are currently at TRL4, meaning that we are researching the technology. It will be interesting to reach at least the technology demonstration, and this is not our area of expertise, but since the project involves robots, maybe other groups may implement our sensor in their system. So I would like to thank you, my work group, which is Real Photonics at UNIGE, Professor Davide Comoretto, who is not here, Professor Paola Lova, who is here, and all my colleagues. I also want to thank the RACE project for the funding, and thank you all for attention, and I'm available for any question. Thank you.
Thank you, Stefano, for your interesting presentation. Are there any questions for him? Okay, I have. Okay, there's one question.
Hi, thank you for the nice presentation. I was wondering that you want to use these photon crystals for the water remediation, for the toluene remediation, I guess, okay. But for example, a curiosity, do you use different pH to try the conditions of seawater? Because seawater has a acid pH compared to fresh water, or also the water that's present near the polluted industries. So, for example, if you have tried different pH conditions in your experiments.
Thank you for your question. It's a very interesting observation. And our study is just at preliminary level, so for now the test is only one molecule and neutral pH. Of course, before testing in actual seawater environment, we need to check the effect of pH, so definitely it will be a test we will carry on. Thank you.
Okay, thank you.
Other questions? I just wanted to ask you how you perform the measurements.
The experimental setup is there is an immersion probe when we put the sensor on, which is basically a small piece of glass with polymers on that. We normalize the water because to check that the water does not provide any shift. And after we introduce toluene in order to observe any variation. And we record the spectra over time.
Okay, thank you. Let's thank again Stefano. Okay, and also this last session is ended. And so I think that we can have lunch now. Thank you again for your attention, and see you at lunch.
giornate macrogiovani sono giunte a conclusione. Noi siamo stati veramente contenti dell'andamento scientifico, perché siete stati tutti veramente molto molto bravi. Di anno in anno, questa non è una frase, un cliché, di anno in anno siete cresciuti tantissimo e quest'anno è stato veramente difficile, molto più difficile degli altri anni. Quest'anno ve la siete giocati sul millesimo di tempo impiegato a presentare il vostro lavoro, quindi complimenti a tutti quanti. Questo è da dire perché insomma a noi non piace tanto decidere fra il più bravo e il meno bravo. Siete stati veramente tutti bravi, purtroppo siamo stati chiamati a fare una scelta e quindi in bocca al lupo per i prossimi premi, perché sicuramente arriveranno per tutti. Detto questo, gli organizzatori vi informeranno su dove il prossimo anno si terrà Macrogiovani, quindi spero di vedervi tutti quanti e di sapere che magari chi non è venuto ha avuto qualche posizione in qualche azienda o all'interno dell'Accademia o del CNR. Speriamo CNR, perché io sono CNR, quindi tifo per il mio ente. Detto questo, iniziamo con i premi dedicati alla memoria di Doriana. Molti di voi conoscono Doriana. Ci tenevo particolarmente che uno dei ragazzi del comitato organizzatore, che ha vissuto con lei i momenti belli di Macrogiovani dello scorso anno, ma anche della scuola a Bertinoro, consegnasse questi premi. E questi premi, che sono stati divisi come al solito per categorie, in questo caso andranno a uno studente e a un ragazzo che in questo momento, o una ragazza, non lo so, in realtà io non li conosco tutti i premi, che sta frequentando il primo anno di dottorato. Quindi lascio la parola a Stefano.
Grazie Sabrina. Io prima di consegnare i premi voglio però aggiungere un qualcosa a quello che hai detto, perché io, come anche altri ragazzi qui in sala, abbiamo conosciuto Doriana grazie all'IM e questo secondo me è una cosa molto importante, che in un evento così vissuto va ricordato, nel senso che IM è un modo sì per la scienza, per far conoscere quello che si fa, per creare un network, però va oltre e, come ha detto anche il professor Giorgini all'inizio, l'IM è un modo per creare amicizie, per creare legami che trascendono l'aspetto professionale, e quello che avevamo noi con Doriana era sicuramente un'amicizia nata grazie alla scienza, e quindi sono emozionato anche a dare questi premi in sua memoria. Allora vogliamo premiare per la categoria studenti Luca Spagnoletti. Allora ci spostiamo, iniziamo con i dottorandi. Vince per la categoria dottorandi primo anno Erika Laguzzi.
Allora, noi vogliamo anche ringraziare la mamma di Doriana e dire che questi due premi, sono stati supportati da loro, dalla famiglia di Doriana, che ci teneva tantissimo ad essere presente a questo evento, perché Doriana, tornando a casa da Macrogiovani, era entusiasta e quindi aveva parlato con la famiglia e la famiglia si ricordava di noi, e quindi io voglio ringraziare Gianna per essere qui e anche Paola, la sorella che l'ha accompagnata, e per piacere un applauso e poi continuiamo. Grazie. Bene, invito la professoressa Coltelli perché gli altri premi invece sono stati supportati in memoria della professora Aglietto. Allora, noi oggi abbiamo visto il professore Pedemonte, però i pilastri delle scuole di Gargnano, i pilastri delle scuole IM e di Macrogiovani erano due professori. C'era anche il professor Aglietto, che era il segretario amministrativo e di cui attualmente cerco di fare le veci, ma in maniera non così, insomma, brillante, così come invece lo faceva lui. Il professor Aglietto, quando la mattina, il ricordo vivo che io avevo, perché io avevo il terrore dei professori, non è più così come adesso, c'è un rapporto molto più conviviale con gli studenti, c'era questa campanella alle 8 e chi scendeva alla fine e chi arrivava alla fine a lezione, insomma, era guardato un pochettino così, ecco, hai perso tempo, cosa stai facendo? Già il docente in aula e sta iniziando a spiegare. E questo è il ricordo che da una parte in quel momento mi terrorizzava, ma adesso mi fa tanto sorridere. La professoressa Coltelli, sua ex dottoranda, porterà un ricordo e dopodiché daremo tutti i restanti premi. Prego.
Grazie Sabrina. Allora, dunque, iniziamo questo ricordo. Nel pomeriggio del 27 settembre 2021 è mancato Mauro Aglietto, professore associato dell'Università di Pisa, in pensione dal 2007. Quindi tutto il Dipartimento di Chimica e l'Università di Pisa si sono stretti attorno alla figlia Anna, alla moglie Svetlana, tutta la famiglia. Vorrei ricordare Mauro Aglietto con le parole del professor Francesco Ciardelli, professore emerito dell'Università di Pisa, ordinario del gruppo di macromolecole nel quale il professor Aglietto ha lavorato. Lui dice: ho avuto la grande fortuna di incontrare nel 1965 Mauro Aglietto al suo rientro in Italia dopo i suoi studi svolti all'Università Lomonosov di Mosca, dove aveva anche conseguito la laurea. Introdotto da Pierluigi Luisi, che aveva rapporti di collaborazione con la loro Unione Sovietica, Mauro venne al nostro dipartimento e svolse un periodo di collaborazione come postdoc nel gruppo del professor Lido Porri, da poco chiamato a Pisa come professore ordinario di chimica macromolecolare. Al ritorno di Porri a Milano nel 1974 si unì al nostro gruppo, collaborando attivamente sia alle ricerche che all'attività didattica e formativa di molti studenti. Tra le sue attività di ricerca ricordo essenzialmente la funzionalizzazione di poliolefine nel fuso, in particolare il grafting di anidride maleica al polietilene, che oltre a un notevole successo scientifico portò alla realizzazione di un brevetto industriale a suo nome per conto della società Replast, che poi portò alla costituzione di Hauser Polimeri, oggi azienda internazionale che produce il Compoline, appunto polietilene funzionalizzato che è venduto e usato in tutto il mondo. Quindi di tale argomento, insieme a molti altri, ha continuato a interessarsi fino all'ultimo. Mi preme comunque ricordare come successivamente si fosse dedicato al riciclo delle materie plastiche, che conduceva sia con rigore scientifico che con enorme passione per la difesa dell'ambiente. Non posso inoltre non ricordare il suo ruolo determinante nello sviluppo della Società di Chimica delle Macromolecole, AIM, di cui è stato a lungo segretario ed organizzatore fino a portarla come membro importante nell'European Polymer Federation, EPF. Il suo interesse verso le persone e la società lo hanno anche portato a contribuire in maniera significativa alla nascita della spin-off SpinPet, di cui è stato fino all'ultimo socio attivo e interessato. Quindi la sua scomparsa lascia in me e in tutti quelli che lo hanno conosciuto un grandissimo vuoto, che solo il ricordo della sua generosità, onestà e desiderio di fare anche per gli altri potranno lentamente colmare. Mauro resterà sempre nei nostri ricordi e nel nostro cuore. Queste sono le parole del professor Ciardelli. Quindi il professor Aglietto è stato mio relatore di dottorato, quindi un riferimento scientifico per me, però abbiamo condiviso molti interessi legati anche all'ambiente, alla passione civile. E quindi vorrei segnalare le competenze che il professor Aglietto ha maturato nel settore dei rifiuti. Questo lo portò poi a attivare un corso presso l'Università di Pisa, che poi dopo il suo pensionamento ho avuto l'onore di portare avanti. In uno degli ultimi messaggi che ho ritrovato nella mia posta e che ho ricevuto da parte sua, mi diceva di aver mandato una lettera ad un quotidiano, perché questo quotidiano in un inserto aveva pubblicato un articolo nel quale si diceva che era più conveniente produrre contenitori per bevande in vetro che in plastica. Quindi questo è un passaggio che lui ha scritto. Il riscaldamento globale del pianeta è un problema che non ci riguarda? Ma chi ha deciso che si debbano sostituire tutti i contenitori di plastica con contenitori in vetro? Ma perché devo andare a prelevare l'acqua del sindaco con contenitori in vetro e non in plastica? Pensate proprio che una persona anziana decida di andare a raccogliere l'acqua del sindaco con contenitori in vetro molto pesanti e non con contenitori in plastica? Ci si è dimenticato che dobbiamo rieducare le persone ad una seria raccolta differenziata e ad un recupero e riuso delle materie plastiche. Soprattutto dobbiamo far capire ai cittadini che si debbono comportare civilmente e non gettare la plastica lungo gli argini dei fiumi, sulla spiaggia e in mare aperto. Questo è il problema più importante, la rieducazione. E veniamo alla questione fondamentale, l'importanza delle materie plastiche e la loro impossibile sostituzione per molte applicazioni. Parto dal settore più importante per tutti noi, la medicina. Pensate sia possibile trovare dei contenitori diversi dalla plastica per il sangue delle trasfusioni? Ci sono poi tantissimi settori applicativi dove l'impiego delle materie plastiche è ormai insostituibile. Vi consiglio di consultare 2 persone per una seria intervista per il vostro prossimo numero di settembre. Il professor Gaetano Guerra, presidente della Società Chimica Italiana, il professor Michele Laus, attuale presidente dell'Associazione Italiana di Scienza e Tecnologia delle Macromolecole, e la terza persona che vi consiglio di intervistare è un responsabile del laboratorio del sangue e delle trasfusioni di qualsiasi ospedale italiano. Si firma professor Mauro Aglietto, professore in pensione dell'Università di Pisa, esperto nel settore delle materie plastiche, Pisa, 2 agosto 2019. Come vedete, queste sue parole ci invitano, come ricercatori nel settore delle macromolecole, a avere un atteggiamento attivo che eviti nella società derive prive di fondamenti scientifici. Attraverso lo studio e l'approfondimento possiamo da un lato proporre nuovi processi e materiali basandoci su sperimentazioni robuste, dall'altro partecipare attivamente a quanto avviene nella società, partendo prima di tutto dai nostri comportamenti, ma non abdicando al dovere di rispondere nel settore dei polimeri a dichiarazioni e scelte che talvolta sono antiscientifiche e irrazionali. Quindi il professor Aglietto si è fatto grande promotore della redazione di libri divulgativi di AIM e anche di Macrogiovani, proprio per coinvolgere i giovani il più possibile in questi percorsi basati sulla conoscenza, che sono non solo professionali ma di vita. Siamo quindi certi di aver raccolto gli spunti che lui ci ha dato nel fare la raccolta di fondi che ha permesso di erogare delle borse nell'ambito di Macrogiovani. Infatti l'eredità che Mauro ci lascia è molto grande e possiamo raccoglierla solo lavorando con impegno e passione tutti insieme, ma soprattutto coinvolgendo i giovani. Grazie.
Grazie. Allora cominciamo con le premiazioni in memoria del professor Aglietto. Per la categoria assegnisti laureati, Emma Contini. Continuiamo con la categoria dottorandi del primo anno. Andrea Giovannelli. E poi Luana Di Lisa. Intanto chiedo ai vincitori di rimanere in zona, che poi facciamo una foto tutti insieme. Va bene, passiamo ai dottorandi del secondo anno. Carlos Pavon. Va bene, per il terzo anno invece quest'anno c'è stata una grande afferenza, quindi abbiamo 3 premi. Il primo è Alessandro Sorze. Andrea Escher. e Valentina Dini. Va bene. Allora, l'ultimo premio per la categoria post-doc invece va a Cecilia Velino. Grazie.
Mi ricordano di dire che quest'anno i premi sono di 300 euro perché abbiamo deciso di suddividerli per più persone e quindi vabbè, la maggior parte di voi che sono giovani sicuramente rientreranno in questo range per la partecipazione ai congressi, sicuramente IM, ma anche tutti i congressi che gravitano intorno alle scienze macromolecolari. Prima di fare le foto di rito con tutti i vincitori, ok? Io sono senior, quindi qualche cosa la dimentico, il supporter dietro. Sì, certo. Allora, bene, volevamo ringraziare nuovamente il dottor Nicosia perché il suo supporto, prego, al centro è standing ovation per piacere, perché senza lui tutto questo non sarebbe stato possibile. Ma insieme ad Angelo noi abbiamo avuto altri due angeli che sono il signor Gancemi e il signor Gatti. E ovviamente le ragazze della segreteria. Adesso, prima sempre delle foto di rito, bisogna annunciare dove il prossimo anno sarà tenuto il convegno Macrogiovani, e però lascio all'organizzazione locale questo piacere, quindi l'organizzazione locale casca qui.
Grazie Sabrina per il microfono. Allora, sono lieto di annunciare che Macrogiovani 2024 sarà a Bologna, grazie al patrocinio di Dipartimento di Chimica Industriale e di Chimica. Vi aspettiamo, speriamo di fare un evento altrettanto bello come quello di questi giorni. Ho imparato tante cose da Angelo, quindi spero che magari riusciamo a emulare qualcosa di simile. Spero che veniate numerosi, Bologna vi aspetta.
Ma i senior sono invitati o dobbiamo aspettare il 30°? 30°. Allora abbiamo deciso che, visto che noi abbiamo voglia di rivederci e non possiamo aspettare il Macrogiovani Gold, il prossimo grande festeggiamento, così come suggerito dal Picchioni, sarà fra 5 anni. Quindi fra 5 anni nuovamente senior e younger tutti insieme, ok? Bene, le foto, prego i vincitori di avvicinarsi per le foto. Vi ringrazio a nome del Presidente Laus e del Vicepresidente Daniele Caretti. Grazie. Sì, ok. Sì, ma la signora è molto provata, io non lo so se vuole, perché non ha voluto parlare, no? Prende la metto quella di... Sì, va bene, ok. Dopodiché faremo una foto tutti quanti insieme, quindi restate perché cercheremo di sistemarci al meglio per essere tutti presenti sulla foto che poi posteremo sui social. Silenzio religioso, che sta su... Oh, è una foto, ridete, dai, forza! Luca Spagnoletti, dai, un pochino di... Felicia? Un po' d'allegria. Eh sì, difatti, ok. Tutti giù, via, tutti giù. No, ma ci stiamo con la immediata. Tutti giù, dai. Tutti giù. Dietro. No, dietro ce la facciamo. Se ti allontani. Se poi volete andare a mare, magari sbrighiamoci e poi si va a mare. Via. Sì, sì, dai, mettiamo... I senior giù, postazione seduti. Anche per... Vieni qua.